Okay, welcome everyone to the 106th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Emanuele Macri from Paris-Saclay, and he will be talking to us about deformations of D-structures.
All right. So yeah, thanks again for having me here. It's great. And yeah, again, we apologize that Paolo talked about this 2 years ago and the paper is not out yet. But hopefully will come. Hopefully will come soon. The issue that indeed the project actually went on, we are adding much more stuff actually. We are presenting it in different ways. And in particular, one of the spin-off of this project that we had was this part about try to make an actual statement. So let me just try to make this statement once and for all, and then we'll discuss about what result actually we can prove. Okay. So I won't speak about the condition. I will speak only about T structure in this talk. So it's mostly algebraic part. And so yeah, so this is joint work. This is a spin-off of a big project that we have with Chuni Li, Alex Perry, Paolo Stellari, and Xiaolei Zhao. But in the spring we were in MSRI in Berkeley, and yeah, with Alex and Paolo we just figured one thing which is slightly different from it's not needed in some sense, but it's slightly tangential, and that's what I'm going to talk today. So okay, so here is the conjecture that we have. So let me start with that. I will explain a bit, but so the conjecture is the following. So I start S to be some base scheme, which let me say nice base scheme. Nice doesn't need to be smooth, but I will tell you in a second what the right assumption will be. And so let me first state it geometrically. So I take X over S to be proper. We're going to change and generalize this thing and flat. Okay, so over S. And so the statement of the conjecture is the following. Then what we expect, you expect that there exists an algebraic space which is kind of horrible. Okay, so it has no particular big structure, but the only thing important, I call it Tx over S. The important thing is that this algebraic space is étal over the base. So Tx over S comes with a morphism over S, which is étal, and which I can describe certain morphism as follows. So which admits a functorial bijection as follows. So it's let me call it tau as the functor. So T is when I apply to some spec of A. So this is going to be the same thing as the following, as bounded T structures on the category dB of the base change XA, which have the property that this category has Noetherian hearts. That this is fundamental for us. And then here A is supposed to be for all spec A over S, which is a finite type. Okay, so that's our conjecture. Okay, so this is with Alex and Paolo. Okay, so what does it mean concretely? Concretely means the following thing: if I give you a T structure on a point of S, then this means that I can lift it with uniquely, at least, in a small neighborhood of the point. Okay, so in some sense, T structure are unobstructed. Okay, as long as and not only unobstructed, they're just unique. This lift, as long as the heart is Noetherian. Okay, so that's the conjecture. And well, we were hoping to present a theorem. We cannot, but we can prove most of this conjecture. So let me make a few remarks of explanations about this conjecture. So explanations. So the ring nice, well, for example, I want, so what I mean for S to be something nice, I want, for example, to be, well, the way that we want is that we will want to apply Artin's criterion, which we'll recall in a second. And so we want S to be suitable to apply Artin's criterion. And so, for example, S could be an excellent scheme, for example. So that's an example. There are some lesser assumptions, but let me assume this one. So in particular, for example, anything which is quasi-projective over or finite type over Z or over any nice string that we like will work. Okay, so anything is good somehow. And so that's where the basis I want. So now let me explain a bit this statement actually. So what is a T structure? So I think I don't need to explain much, but let me just do very quickly. So a T structure is just for us it will be just a pair T tau, which is D smaller or equal than 0, D greater or equal than 0. On a triangulated category. At the moment we don't need any announcement, which I call it D, and which has the following properties. So let me just go a bit further, which has the following property. So the first one, I want that it's closed under the shift. So the D smaller or equal than 0 is contained in D smaller or equal than 0. And generally, this thing is called by some classical analogy, D smaller or equal than -1. So there is a sign. Then the positive part is just the orthogonal to the negative part to the left. So anything smaller than 0 goes to something which is the morphism from there on is 0. And the third one is, okay, there is an exact triangle for all elements in D. I want something which is of the form E smaller or equal than 0 goes into E greater or equal than 0. Oh, sorry, greater than 0. Okay, or if you want it to be precise, greater or equal than 1. Okay, so that's what we want. And so one of the nice properties of this thing is that if you take the heart, which is D smaller or equal than 0 intersected D greater or equal than 0, this is an abelian category. And so it makes perfect sense to speak about notariality. Okay, so that's Notarian in the usual sense. So this makes sense. Okay, so that's the first adjective that we saw in this statement, which is Notarian heart. So I just want that every object, if I take a chain of sub-objects, this chain stabilizes. Great. So that is the first two explanation for the base has to be sort of nice, but as general as possible.
Emanuele,
Sure.
the second bullet point,
Sure.
should one of those be -1? The second bullet point.
The second bullet point has to be. I'm sorry. Thanks. Great. Thanks a lot. Indeed.
Okay, yeah. So
Thanks. Sure. Thanks, Justin. Yeah. So yeah. So that's the definition. So notarianity makes sense, and so bounded. So bounded. If you look at the standard definition of in the book by Beilinson, Bernstein, Deligne, and Gaber. So that's slightly different. For us, we also want non-degenerate in the same definition, and so this is given as follows. I just wanted D to be equal to the union of all A smaller or equal than B, then D greater or equal than A, intersected D smaller or equal than B. So just for later use, it's not important. It will come in our paper, but it's not super important. Non-degenerate actually is useful for us. This means that the cohomology, given an object, I can look at the cohomology objects because the T structure is like having complexes in some sense. So cohomology objects are well defined. And so I just wanted that if something has a zero cohomology, it has to be 0. Okay, and so that's the notion of non-degenerate. And bounded means bounded cohomology. These two conditions together are exactly what we have in this condition here. Great. So bounded, we are good. So we are all, so I think everything in the statement now should be sort of clear. Let me go back to the statement now, a second. So why do I need Noetherian? Because if it's not Noetherian, then it's easy to find counterexamples. So there is a procedure called the tilting, for example. And if you start from P1, you take coherent sheaf, which is the classical example of something with a Noetherian heart, and then you just do a tilt at the point. Then this structure is non-Noetherian. And okay, if I vary the point, this structure varies continuously. So it's definitely not at all. Okay? So this means that really Noetherianity assumption is what is fundamental for this theorem to be true. Second thing, there is this part about dB. So here is a general X with base change over a general affine scheme, which is a finite type. Okay, but okay, still a general thing. So we could decide some other categories. We're going to see a bit later. But in some sense, we can choose perfect complexes, for example. And perfect complexes won't work because in general, unless the scheme is regular, there is no T structure on perfect complexes. Or we can look at quasi-coherent sheaves. There is plenty of T structure, but there are too many. Okay, and so the theorem is probably false. Actually, I don't have a counterexample now, but it's clearly false on quasi-coherent sheaves. So dB is really the place where is the only place where this theorem can be true, and the Noetherianity assumption is the only assumption that has a possibility of this statement to be true as well. Okay. So great. So that's a statement. Okay. And let me make another remark about that. So why do we came up with this statement? Because this was very much inspired, but by a paper compares with some result by Bellmans, Okawa, and Ricolfi, where they have the same identical statement, but now for semi-orthogonal compositions. Okay. They have some assumption, and then we'll talk a bit later. So their assumption is that X over S is also smooth. Okay, we'll see that in a second how to change it. So they have the same statement, and semi-orthogonal composition, this seems harder because you're trying to parameterize. So it's the same identical statement, okay? They seem harder, but in some sense, generally, there is always this duality between semi-orthogonal decomposition and T structure. And the two statements generally are somehow, whenever you can formulate some nice statement at the level of semi-orthogonal decomposition, there is generally an analog statement at the level of T structure. The only thing is that generally the statement of T structure is harder to prove. And the reason is very simple. We'll see later in the proof. Somehow, semi-orthogonal decomposition actually depends only on finitely many choices, while T structure, a priori, they do not. And that's what all cause all the problems, and indeed also for us. That's one problem. There is other problems that I'm going to tell a bit later. In any case, that's their statement, okay? They also have some conjecture somehow. They conjecture that the statement should be true under in more generality, and that's actually what we prove as well. Okay, so one consequence of our result is that we will prove the conjecture in the case of semi-orthogonal decompositions under much more general assumption that we'll recall a bit later. Okay. Anyway, so that's about the statement, and now let me say how to prove it. So it's a conjecture, so there is no proof, but let me try to say how to approach. And again, the idea of this proof is just goes back to their paper, and so let me just go through it. So idea of the proof. Okay, because if you want to be more correct, how can I approach this? And so the only way to do it, as they do, is to use Artin's beautiful criterion. And so what he's telling you is telling you that this kind of statement is true, but there are essentially 4 conditions to be checked. So the first one, which in this case, in the case of T structure, while for semi-orthogonal position, this is actually clear, but for T structures, it's not at all clear that the way that I define the functor, so Tx over S, is actually a functor. So let me go back a second. So if you look at this part over here, there is no reason why this is functorial. Okay, at least not in this generality that I wrote here. Okay, so that's the first part. The second part, that once it's a functor, then you have to check something which is pretty standard. So you have to check that at least the right-hand side, it's a sheaf with respect to the detailed topology. And the second condition is what artists call the locally finite presentation. And so what does it mean concretely? It means that whenever I am in the context of the right-hand side, okay, then I want that if I take a co-limit of algebras, and that this is also an algebra of finite type, so I want that this commute with co-limits of the set. So if you want to just union. Okay, so that's what it means. So now it's standard. Once you have this one at the level of affine schemes, then it's just a standard condition that once you have this one with some epsilon work, you can just extend it to all sheaves, to all schemes, sorry. So if I have 0, 1, and 2 on all spec A over S, then we can extend the definition. So let me just give a name to this thing, since I'm always referring to it. Let me call this thing star. So this is the part on the right. So once I have this definition, I know it's functorial, I know it's a tal local, behave nice, a sheaf with respect to the tal topology, and I know that it behaves nicely with respect to co-limits, then I can extend it to all schemes. Okay, and the interesting thing is that still it will satisfy, still has properties 1 and 2. Okay, so we are pretty good. So once we have these three properties, then we have it for all schemes. The only thing is that we don't know how it's defined. So the way it is defined, we just use this formula, take some scheme, you realize there's a limit of things of finite type, and then you define by this formula what the functor should be. Okay. Good. So, and now comes the fourth question, the fourth condition in the criterion, which is the hardest of course. It's just if I take a Bm, so this is the local Noetherian ring, which is emadically complete. It's complete with respect to M. With, if you want, an extra small property that spec of B modulo M, when I go into spec of B, and then I go into S, so this composite map must be of finite type. So at least I do have the description that we had before, at least for B mod M. Not for B, B is not finite. And so the condition that I want is the following. Then I would like that, I have a restriction map, it's functorial. So I have a map from Tx over S of B into Tx over S of B mod M. So restricted to the special point. And so what is the condition of Artin is that this map is bijective. Okay, so that's a criterion of Artin. If these 0, 1, 2, 3 are satisfied, then the conjecture holds. Okay, so that's how to prove this statement. That's how Ricolfi, Bellman's, Okawa, Ricolfi prove their theorem. Okay, great. So what do we prove? And so here is the first part. So the first part is actually pretty easy because in some sense was essentially already done by Polishuk. So the fact is a functor, we need an epsilon modification of what Polishuk did, and the fact that it's a sheaf with respect to a tal topology of this local finite presentation is essentially in the work of Polishuk. And so let me state this as a proposition, is that 0, 1, and 2 holds. Okay, so that's fine. Okay, so that's all good. So the only thing we need is 3. Okay? And so 3, we have a problem. But on the other hand, for all applications that Paolo talked 2 years ago, we don't need really 3. Somehow this statement is nice as it is. It will be nice to have it once in the future you would like to study, for example, moduli spaces of some certain nice categories. But for application, actually, the only thing we need is that at least we can deform T structure. And so what we can prove, well, we can prove the following statement. So this is the theorem that we have. So main theorem. And this again is joined with Alex and Paolo. And so take BM as above, as in 3. Then I define a slight variation of what we have before. So I define T prime of B as follows. So I define it as in condition star. So I define it as bounded T structures on dB of XP with Noetherian heart. And so the issue is the following, is that a priori, this is not T of B, okay? A priori, T of B is defined by the condition as a co-limit, right? So a priori, this is not equal to tau B, but we prove the condition 3 for this definition. So the theorem is that then you still have a restriction map from Txs prime into now T of xs B mod M. And what we prove that this map is bijective. Okay, so that's the theorem we prove. And so what does it mean? So this does not prove the conjecture. Indeed, it's still a conjecture. But why does not prove it? So in some sense, the following. So that what does this theorem say? This theorem says that given a T structure on a point, formally I can lift it. So that is good. Now, to prove actually the statement of the conjecture, we will need to prove that whenever I have it on a formal level, I have it some sort of at some sort of actual neighborhood in some sense, at least at all locally. And for doing that, somehow each object in this structure is defined on some nice neighborhood. But okay, I have a priori infinitely many objects in this T structure. This T structure, even if I start with something that is only finitely generated, a priori this T structure we have will not be preserved this condition. And so we can do it. Each object can lift, but a priori we have infinitely many objects, and so a priori we don't know if the whole T structure is defined on some neighborhood. Okay, so that's the problem. For semi-orthogonal decomposition, there is no problem, because in that case, a semi-orthogonal decomposition only depends on the projectors. And the projectors, they are finitely many. Okay, so once I lift all the projectors, I lift everything. And so the same proof, actually, that I just told you, actually does reprove, if you want, the theorem by Bellman's, Okawari, Colfi. I can generalize it. Okay. Anyway, so that's our main theorem. And yeah, unfortunately, somehow for the conjecture, it's even the question is even open for simple cases. For example, I can take B as a complete as a DVR, for example, and then I take B hat as the completion. And then it's already unclear. So I have a T structure on the completed one. How can I induce a T structure on the actual DVR? And so that we don't know how to do it. Okay, so that's in some sense is the baby case. Okay, the baby case is just doing that. If you're able to do that, then I guess somehow in some way we can at least we can prove some part of the conjecture. All right, so I think I'm at half an hour. So what I want to do now, so this is the theorem. I think I explained a bit the conjecture that we have. Motivation, but motivation actually somehow, once we can deform T structure, is actually nice because our setting is sort of general, right? So you can imagine that this B, I have no condition on this B. Could be anything complete. So of course, for example, we want to apply, for example, to something geometric. So it could be a local ring completed of a curve in a family of varieties. And so this means that once I have something on a point, I have it on a formal level. And so once I have it at a formal level, I have it on the very general fiber. Okay. And so this is useful for things that we are interested in terms of stability conditions. So one of the problems of stability conditions is to construct them. So this theorem is telling you that once I have it at one point, then I have it on a family. I have it at the very general point. Okay, so that's and for that we just use this statement at the level of complete DVR. So yeah, so that's one application. We have other applications somehow nowadays. So it's we can solve some conjecture by Kuznetsov, Shinder. There are many applications just of this theorem. Okay, so that's but still somehow the proof of the actual conjecture would be nice, and we are not there yet, unfortunately. Anyway, so what I do want to do in the last half an hour, I just want to present a bit the proof of this theorem. Okay. But to present the proof, actually, and for application, somehow this setting is not enough. Okay, so I need to do a bit more, and so let me try. Okay, so we have to start settling really what the correct setting is, what are we using it, and so let me try. Okay, so I'll try to sketch the proof, but of a general version. All right, so let's start. So what is the setting? So the setting is the following. So I start with a category, and maybe so this will be my dB of x. So I want some condition. I want it to be proper. I want to be flat. So flat is not quite necessary, but I want some epsilon variation. For example, I will be happy if the morphism is finite or dimension, for example. And so in the context of categories, this is easy. This is the notion of a proper category over a base. So here I need some announcement, of course, to speak about the action of S on D. But this relative setting simply means I have some category. Proper means the following. So proper means that, well, there is once I have a relative category, I have a notion of a local home between these two objects. And so the notion of proper means the following, is that for all objects in D, so this object exists. That's a notion of this announcement. And so what I want this object to be perfect on S. Okay, so concretely, if I am over a point, it means that I want all the x to be finite and to be bounded there are only finitely many degrees where is non-zero. Okay, great. So the notion of proper. So in the geometric context, it simply means the following: that I have a morphism which is proper, but there is some flatness embedded into the theory. So indeed, it's finite or dimension. Okay, so if I have a morphism from a scheme into S, under some nice assumption, the category D perf is proper if and only if the scheme is. So let me just write it. Example: if X over S is proper and finite Tor dimension, then essentially this is equivalent to having D, which is D perf of X, to be proper over S. Okay, so the action of S is just tensorization by perfect complexes on the family. Okay, so careful, because the coherent sheaves, which is what we're interested in, is not proper. Okay, so we need to, now we start with perfect complexes, but perfect complexes, they don't have T structure. Okay, so we need to recover in somehow the whole theory out of this category. Okay, so small lemma. This is easy. This is just our proof actually is based on three versions of a lemma by Nakayama, which we all know. And so this is the easiest one. So if I have something which is perfect, so in this category D, and I take a point in our base scheme S such that the base change to little s is equal to 0, then what happens? It happens that there is an open subset U here containing S such that E restricted to U is equal to 0. And the proof is easy because the proof is the usual Nakayama lemma, but applied to these guys over here. Okay, and so that's nothing. Just taking definitions and checking. So there is no hard proof. It's just what I told you actually. Great. Okay, so that's the first lemma, and we record it here. Okay, so a complex is 0. When I restrict to 0, then it's 0 in a neighborhood. Okay, once I have that one, then I define an analog of quasi-coherent sheaf. I call DQC. So for this one, I need an announcement. And this is defined by just adding all inductive limits over D. Okay. And so again, in the cases that, in the geometric case that I just described before, in that case, DQC is just the same as quasi-coherent sheaves on the family. Okay, so this is in the example that I just discussed over here. Okay. Great. So we have quasi-coherent sheaves, which is good, and we have perfect complexes. Now we need bounded thingy. And so how do we do that? Well, now there is a nice theory that we can use, is the following. So let's just start adding some assumption. And so the first assumption I want is the following, is that there exists some generator. Okay, so there exists, but for some applications, I need this generator to be infinite, but there's no problem. So they might be infinite. So I have a family dove alpha are in some family G, which is some set of generators. I can say for D, these are objects in D, it's important. Or for DQCO. So there are two conditions of what it means to be a generator. A generator means at a level of QCO, this means that if I have a home from these guys and the object, if the home is 0, then the object is 0. And at the level of the small category D, this means that is generated by these G alpha, by shifts, extensions, and direct summations. Okay, so that's the condition. So I want this to exist. And the small remark is that if D is smooth and proper, which is the case we are interested in, then this assumption is satisfied. So this is okay if D is smooth and proper. In that case, actually, there is just one generator. And so we can just take, it's not infinite, it's just one. So we can just take one. Okay, great. So once I have this set of generators, now I can define a T structure. And so what is the T structure? The T structure is the following, because I'm free to do whatever I want on quasi-coherent sheaves. Quasi-coherent sheaves, they are super flexible, so I can define as many T structures as I like. And so I can define a T structure on quasi-coherent sheaves just by asking the following. I just ask DQC smaller or equal, and let me call it a G, then 0. So this is the following. So this is just generated by all generators G alpha, where I'm adding only positive shifts, I'm adding extensions, and I'm adding infinite direct sum or arbitrary direct sums. Okay. And I just define greater or equal than 0 as the orthogonal of smaller or equal to -1. Okay. And so the interesting thing is that this T structure is on DQC. This a priori does not descend on anything, but this is useful to get some structure. And this T structure is actually very useful because, well, at least if the generators are just finitely many, so this means I can assume there is one generator as before, then these T structure are all the same in a certain sense. So small remark. So if I take 2T structure, tau and tau prime, then I can say that tau is equivalent to tau prime if there exists n1 smaller or equal than n2, such that the following holds. So d smaller or equal in tau of n1 is contained in D smaller or equal than tau prime of 0, let's say, it's contained in D smaller or equal than tau of n2. Okay, so this is a notion of equivalence between T structures. This is due to Niemann, essentially, somehow. He studied this kind of relation. This is an equivalence relation. And what does it mean that the two T structures are equivalent? Well, it doesn't mean much about their heart. It could be arbitrary. But it's telling you that we can compare at least bounded objects in some sense. And the second thing which is interesting is that in general, they are all in the same equivalence class. So this is somehow surprising result by Niemann, at least in the geometric setting, at least under very reasonable assumptions. And in general, in this context, it's not automatic, but okay, so there is a preferred equivalence class is the class tau, which are equivalent to this tau g that I just defined. Okay, so this is what we need. This is a technical condition. We can compare things, and as I said, when the generator is unique, finite or unique, is the same thing, then they are all equivalent. Okay, so it does not depend on the choice of the generator. So this is a good T structure, actually. Great. So once I have this notion of T structure, this notion of equivalence class, then I can define a definition. Then, so I have G, I have my tau G, and so I can define the category of pseudo-coherent sheaves formally as follows. So these are all objects in quasi-coherent, such that they have the following property. For all M in Z, there exists some triangle as follows. So I have EM goes into E goes into TM as follows. So EM is an element which is in D, so it's perfect. And TM is an object which is a priori just a quasi-coherent sheaf, but which has the property that is sufficiently is contained the category with sufficiently negative degrees. Okay, and so this is really what classically is a pseudo-coherent complex. So a pseudo-coherent complex is something which is approximated by a perfect complex up to something which has very negative cohomology. Okay, and so that's analogous of that. And so for that, I just need a generator. But as I told you, if I take something which is in the same, in the preferred equivalence class, then this category is the same. Okay, so it doesn't depend on the choice of this structure in the same equivalence class. And once I have this category, then it's easy to find what is the bounded coherent category. And this is just all pseudo-coherent, which are bounded below. So, or if you want, which are bounded with respect to tau g. Okay, so I just have a notion. So I just ask that if every object at a certain moment is in some greater or equal than n. Okay, and so this is the category we like now. Okay, so now we have a category, this dB, but actually dPc is also useful for this kind of things, which is the analog of quasi-coherent coherent sheaves, bounded coherent sheaves. And so this we need, because even if you have a smooth category, a smooth and proper category, well, of course, if it's smooth and proper over something which is of finite global dimension, then dB is the same as D. That's good. But if it's smooth and proper over something which is not of finite global dimension, then this has no T structure in general. So we really need to introduce this kind of dB for having a statement to hold. Great. So one small remark. This is sorry. It's just for fun. Is that under our assumption, this T structure, there is we need some nice behavior. So the first thing we have is the following: if something is perfect, then at least it's bounded above. So that's the first small remark. Okay. And to have the category of pseudo-coherent sheaf to be well behaved, well, we need at least that somehow we have nothing that becomes zero, that's easy in all smaller or equal than m. So we need this structure to be non-degenerate. And so this is the assumption. And so what is the next assumption? So this is assumption 2. says the following. Let me write it as follows. For all alpha in G, there exists some fixed M alpha in Z, such that the homes from G alpha to G beta shifted by M are all equal to 0 for all M greater or equal than M alpha. So what is geometric this means? This means that your category or your scheme in the geometric case is of finite dimension in some sense with respect to cohomology. So if you want to satisfy Grothendieck vanishing, okay? So if you want, for example, this means that it's finite Claude dimension, okay? Now the condition I want it relatively, and so the actual condition that I need is the following. I just take the relative one. And but the relative one, then what I want, the condition that how to state it properly, sorry, it's just that this complex is in D, I'm sorry, in the perf of S smaller or equal than M alpha. So if S is affine, it's fine. This is just a technical condition. Okay. So if I write it in this form, it's nice because I can base change as well. But anyway, so this is slightly stronger than the condition I wrote. We need this condition. But if S is affine, they're equivalent. Or if S is finite dimensional, they're equivalent. Okay, great. And so why do I need this assumption? Other remark is that assumption 2 implies that this T structure, as I told you before, is non-degenerate. Okay, so at least nothing will be, there is no weird thing in this category to happen. Okay, so this is really the condition that guarantees that the T structure is somehow there is nothing which has something as cohomology 0, then the object is 0. Great. So now the key result is the following. Once we have this assumption, so the assumption are we have a generator, and this generator has some vanishing in cohomology. And so the second Nakayama lemma is the following. Is a version for pseudo-coherent shifts. Okay, and so a priori here is not clear, but under our assumption is still true. So if I have BM, actually this is true for any local ring. It doesn't need to be complete. It has to be Noetherian, of course. And I take S as a spec of B. Then I take D, which is proper over S. I take G satisfying 1 and 2. And then the statement is that if I have something which is a pseudo-coherent, and when I restricted to B mod M is equal to 0, then the object is 0. Okay. So this is telling that the Nakayama, a version of Nakayama holds in this generality. Okay. So this is not so clear a priori, because as I defined this category DPC, sorry, I go a second up. It's not at all clear that I can do that, but its assumptions are exactly what makes this argument possible. Okay, you need some argument here. It's not completely evident like the first lemma, but this is still holds. All right, great. So again, what are the intuition of these categories? Let me say D is perfect complexes. So this is the nicest category. It's proper, everything is nice, but in general, there is no T structure. Quasi-coherent, they have everything we want. We can do all construction we want, but there are too many. DB is the category we want, okay? And DPC in some sense is the category in between. So it's nice, it behaves nicely. So all construction we do actually will be in pseudo-coherent. And then at the last, we just use some argument to reduce from pseudo-coherent to bounded, okay? All right, so once we have this preliminary, now I can give an idea of the proof of the main theorem. So first of all, let me define what is now. So I start with D over S proper, satisfying condition G with 1 and 2. Okay. And so what is the functor now? The functor is defined exactly as before. I need a bit more attention here. So I want bounded T structures on this category DB. Now this is an answered. I can base change, and I can base change also everything I want. I can base change. I need some assumption further. I need this to be compactly generated. And I need it in the preferred equivalence class. And I need the actual assumption, which is with Noetherian heart. These two assumptions compactly generated in the preferred equivalence class, these are they hold true for the case in geometric case. Here we need to add as assumption. Okay, then okay, let's prove the theorem. So how do I prove the functor? Okay, so this is so I need to prove that this thing where spec A over our base S is of finite type. So how do I prove the functor? So the idea is let me give you some sketch of that. So first thing I want to prove that the tau d over S. So what I have to prove? So I have to prove that if I give you a morphism A into A prime, which is of finite type, and they give you a T structure on A, I can induce a T structure on A prime. And so there are two ways to do that. So it's finite type. So by definition, these factors through something of the form to an extension which is polynomial followed by a surjection, right? That's by definition. And so this one was covered by Abramovich-Polishuk in a fantastic paper. So they prove it exactly what we need. That if I have a T structure with Noetherian heart, they fundamentally use Noetherian, then I can induce something on the affine space over it. And here, Polishuk has another result, which says that once I have something on a variety, I can induce on a scheme. I can induce something on a closed-up scheme, or actually in general on something which has a finite morphism to it. But Sasha had this assumption more that it needs to be of finite third dimension. Well, for us, it's not obvious, and so we need to extend this argument. So plus epsilon, which we do. And how do we do that? Somehow we use Polishuk approach, but as I told you, we do it on DPC, on pseudo-coherent shifts. So there it works. So we get a nice T structure on the pseudo-coherent, and then we work a bit more to extend it to actually prove that this thing actually induces something on DB, if it starts on something on DB. Okay? And so once we have these two statements, then it's fine, and then it's a functor. Okay, so that's a bit the idea. Sorry, I just quickly, because I don't know how much time I have. So this is a functor. Now to prove it's a tal, there is no issue, and to prove that it satisfies. Sorry, here I'm actually sketching more like before the main theorem. I'm actually sketching more the proof of the proposition, if you want. Okay, but anyway. So that's the bit idea. And maybe, let me just now go to the main theorem. The other two properties essentially were proved by Polishuk. And so here is where I really want to prove the main theorem. And so here, we need a third assumption we need. Okay, and so assumption 3, but we have never yet used the fact that that we have Grothendieck's existence theorem. And so for schemes, this is fine, but in general, we have to assume. So if I have local Noetherian complete ring, then what we want to prove, now we want some statement on pseudo-coherent. So I want that there is an isomorphism between this one and the limit of D of B mod M n plus 1 EC. Okay, so this statement written funny, but this means exactly what this is an equivalence. So this means exactly what we need, right? We have these categories, and so I want. So we need that it's a Grothendieck existence theorem. Once I have something which is coherent on each infinitesimal neighborhood with compatible morphisms, then it's something which is coherent on the formal at the formal level. Okay, so this is the theorem, and we want this to hold. Okay. In our context, this is only possible for pseudo-coherent, so that's the assumption we want. And of course, this assumption, it's okay in the geometric context, but also it's okay if the category is smooth and proper. You have to prove it, but it's true. So in the smooth and proper case, we have no assumption. Okay. In the geometric case, we have no assumption, as I stated. In this case, we do need. There is another assumption that it's or geometric. There is another assumption we need, which is a bit technical. So maybe I'll go very quickly through it. And so this assumption is that there exists a strong generator on DBB. Okay, so what does it mean, this thing, actually? So strong generator, if it's not regular, the schema, this is not true, right? There is no strong generator on perfect complexes. There is a generator, but it won't be strong. Strong means that it generates up to finitely many extensions somehow. But the result by Rouquier, originally was Vandenberg, then Rouquier, then Niemann, I think. So in large generality, Aoki, there are several proof of this thing. Bounded coherent sheaf, they do have a strong generator, even if the scheme is not regular. Okay, and so we need to assume the same thing here. And again, by some chance, if it's smooth and proper, or if it's geometric, as I told you, this assumption holds. Okay, so in some sense, if I start the category smooth and proper or geometric, I have no assumption. Indeed, as I stated the theorem at the beginning. Okay, in general, we have to assume all these things. All right, so now how do we do the proof? Okay, once I have all these assumptions, this assumption won't appear in the statement, but let me just mention that we need. So how do we go for the proof? So I take S as spec of B. Okay, and so what is the datum? The datum, I have a T structure, I call it tau 0, which is something in D over S over B, which is defined over B mod M. And generally, I denote this thing by 0. Sorry, let me just for simplify notation, otherwise I have to write B mod M everywhere. Okay, so that's what we want. Now, by proceeding as we saw before in some sense, you can always extend it to a T structure, which I call it tau 0 hat on D 0 Kuko. Okay, so that's a standard thing. And now what do we want to define that category? And so to define the category, we need the following. We define DQC smaller or equal than 0 as follows, as the only possibility in some sense. So it's the category which is generated by all element in D, such that when I take the restriction to the special point, E is exactly where I want. So it's in D0 smaller or equal than tau 0, 0. And then I close it up by direct sum and extensions, infinite direct sums. That's the only definition we can make. And what we prove is that it's not only the only possible definition, it's just a unique definition, because that's actually once somehow this is the Talnes property, right? So it's really unique, this structure. So that must be that a posteriori. Anyway, so the key point here is that this gives you a T structure, we call it tau hat, which is a T structure on quasi-coherent sheaves. And so the whole goal of this is a standard thing that happens everywhere. You have something quasi-coherent, you want to descend it. Okay, and so I want to descend it. Well, the first piece I want is a PC, and then, as I told you, to DB, which is where we want. Okay. Great. And so how do we do that? And we need a third version of Nakayama. And for this lemma, we use essentially this is where the assumption 4 actually comes into play. And so this is the key part. So there is a third version of Nakayama. Sorry, just taking 1 minute, and then I think I'm done. Which says the following: if I have something which is pseudo-coherent and it has cohomology with respect to this strange D structure we just defined, tau hat, in degree maximum 0, then the statement is the following: then the cohomology object with respect to tau hat of E is non-zero implies that the cohomology of respect to tau 0 hat of the cohomology with respect to tau hat of E restricted to 0 is also non-zero. So this is not an obvious statement, right? Because I know that E is pseudo-coherent, so that's all good. But we don't know yet that the cohomology is pseudo-coherent. So in principle, this H0 of tau hat is actually quasi-coherent. And so for quasi-coherent sheaf, Nakayama does not hold. So there is no reason why something is different from 0, then the restriction taking cohomology is going to be non-zero. Okay, so this is the key point of the whole proof is this lemma over here. Okay, so but it holds. And now how does it work? And now let me give you an example, and then we finish the proof is easy. So let me just give you an example of B as the standard power series ring, C of T. And then it's easy to find a sequence which is actually annoying from respect of several things. I just take C of T, then I embed into C in the Laurent series, and then I take the quotient of it. That's an elementary example. And so what is the problem? The problem is that a priori in modules over C of T, it could happen that you have a T structure where this sequence actually it's annoying. And so, for example, what can happen? It can happen that this thing transforms as follows. So I have my CT, which is some nice coherent module, of course. Then this guy goes into CT, and this becomes the cohomology in degree 0. And then it goes back, and then it goes into something which is this quotient here, C of T modulo C of T, and then I shift it by -2, for example, and then I shift it by 1. And so this will be H minus 1. Okay, this structure exists, actually. And but the point is what? How do I use the lemma above? But this structure cannot arise by one of the one we just defined. And the reason is this Nakayama lemma. Because the point here is that if I take this object and I restrict it to the 0 fiber, this thing is 0. Okay? And so this condition of Nakayama lemma is not satisfied. So this T structure, if it exists, it won't be one of ours. Okay? And so what is the whole point here is to prove that this thing does not arise. Okay, so that's the whole point of the proof. And indeed, it goes through. So let me finish it. So key point is the following. So if I start with E, which is, let's say, DPC intersected DQC smaller or equal than 0, tau hat. Then I take A as the cohomology in degree 0 and assume it's non-zero. Okay, so it's in the heart. And so what is the key point? I can use, in some sense, assumption 3. Now I can use the fact that I can take limits to show that there exists an exact sequence in the heart, which is the following. It's 0 goes into A hat, goes into A, goes into A bar, goes to 0, where these guys have the following. So this guy has the property that if I take cohomology of this A hat and then restrict it to 0, this is 0. And here I have something which is in the heart intersected with pseudo-coherent. And this is easy to construct. This is just a limit of the restrictions. Okay. And now once you have that done, we are done. Because in some sense, take this 8, this is coherent. So take the composition, you get something coherent with a property that the homology is non-zero, but the restriction is 0. And so by using Nakayama tree, this shows that A hat is 0. And so that the homology of E is pseudo-coherent. And so we are done. Once the homology is pseudo-coherent, then I proceed by induction, and I prove that everything is pseudo-coherent, so that this structure descend. And then after that, you prove that it's unique, and so on and so forth. Sorry, I think I'm out of time. So sorry, I was a bit quick in the last part, but I'm done. Thank you very much for the attention.
Thank you, Emanuele.
Thank
Can we all mute ourselves and give Emanuele a round of applause now?
you.
If you have any questions for the speaker, please ask them now.
Technical.
Can I just say something about the strong generation thing? I mean, of
Sure.
course, there are lots of cases where DB coax has a strong generator without
Sure.
X being regular, but
Yeah.
that's not, I mean, there are also cases where DB coax does not have a, I think the most
Yeah, but by
sophisticated,
Niemann somehow, these are very degenerate case, right?
I think the
essentially-
most,
if
I
it's
mean-
proper over an excellent ring, then it's always
okay,
true.
yeah, that is true. So in your case, that is true.
Yeah,
So therefore
so-
you have a strong generator.
But in general, if you remove the assumption of excellent, even Artin's criterion, somehow Artin criterion goes through in Stack's project. If you look there, they have the assumption that the rings are just you just need this condition that Popescu's theorem holds, right? Which is that the map from the localization into the completion is geometrically regular.
I think,
So yeah, you can imagine that maybe the theorem goes through under this assumption, but unclear somehow.
yeah, for quasi-excellent separated
Yeah,
schemes
basically-
by a dimension, the DB does have a strong
Yeah, I
generator.
think some of this theorem is result by Aoki.
Okay.
Yeah, that's actually what we use here. Actually,
Yeah.
that's the same strategy. That proof is absolutely generalizable to this context as well. So that's actually how we prove it. Actually, so in the smooth and proper case, the smooth and proper. So so that yeah, so that actually, yeah, that's probably what assumption you want. But in this general context, it's not so clear that the categories have strong generator. I'll make you an example. The classical example that can apply this theory is when you take supported categories, right? And so category with support, those are annoying, right? So if the total space is smooth, those they don't tend to have, if I don't mistake, they don't tend to have strong generators.
It's just that, I mean, because you were maybe running out of time there,
Mhm.
maybe you're thinking about time. So you said very quickly that DB has a strong generator. I thought you were maybe trying to say that it always has a strong generator.
No, not always, not always. No,
So
no,
I
no.
just wanted
It has it. Sorry, let me go here. So this is assumption. We have to assume that.
Oh, that's an assumption.
It's
I'm
an
sorry.
assumption for, yeah. So we have to assume that there is a strong generator, and it's always true if the category is smooth and proper,
Yeah.
or in the geometric situation.
By modifying cause result.
By modifying Aoki's proof. That's correct.
Yeah.
Yeah, and it's actually the same proof. The same proof goes through, but you need to be more careful because someone uses smooth and proper to essentially. You need to prove that there is this paper by Benz V, Francis, and Nadler that essentially they prove this interesting statement that dB can always be realized at dperf tensored over a base with dB co. So something of this sort. And so we need some analog in this context. But once you have that one, then the proof of Aoki goes through without any effort. Yeah, so it's the same proof.
There's actually now a non-commutative version of that statement.
That's correct. It's a non-commutative, but only the smooth and proper case. So that statement I told you, we need D to be is called dualizable somehow. That's what people use as a terminology. And so this we need. I actually need it. Otherwise, it's not true. So the statement I told you is not true, and yeah.
Okay.
So, but we can only prove it in this context, smooth and proper. Or geometric, but geometric is just that was already known. Yeah. So these four assumptions, in general, we have to assume them. They're not automatic, and I think there is somehow I don't have now a counterexample to each of them, but somehow it's clearly they're not satisfied in general. But in the smooth and proper case, we have no assumption, so that's important. So it's just if you have a smooth and proper category over a base, which is nice, then the theorem holds. Yeah, then you can deform the T structure without any abstraction.
Any other questions?
And yeah, and maybe the same proof goes for similar orthogonal decompositions by proving, for example, a conjecture by Bellman's, Okawa, and Ricolfi. Yeah, that's
If there are no more questions, can I ask one small, just clarify something small? So of course, if there is a single generator, you get this preferred equivalence class, and you did mention it, but is that the only place where you are using the fact that there is a single generator whenever you're using preferred equivalence classes?
So the single generator, we only need, somehow it's not needed that we have single generator, but somehow somehow the only thing we need, is that, yeah, the preferred equivalent classes is nice. Yeah, so once we have a strong once we have only one generator, then whatever generator you choose, the T structure induced are in the same, they are all equivalent. So that's nice. And also, if the category is smooth and proper, we can prove an analog of what Niemann proved. Niemann proved that essentially on the geometric setting, all T structures are in the same equivalence class. It's a fantastic result. And the same is true also for smooth and proper.
And can I just say, this is not a question, but this thing that you have on the screen right here, that if you have who to cite for the theorem. So we often cite Alonso, Jeremias, so then Leo is in the audience just now, so I just wanted to.
Okay, sorry, yeah, that's correct. Yeah.
Just wanted to mention
sorry,
it.
I didn't quote properly. So this is a theorem of them, indeed.
Yeah,
that's correct. That's hi. Exactly. So actually, I'm using it several times, this theorem. Somehow I'm using it here, and I'm using also when I'm extending every time I extend something from DB into the whole category with the theorem.
Yeah. Actually, I mean, that has been discovered recently. Aihara and Yama proved this theorem without citing Leo and his co-authors in 2012. And Lurie proved this also without citing.
It's reproved several times, it's true. Yeah, that's definitely somehow.
Yeah,
it's very useful. Actually, it's somehow where I learned from this paper by Polishuk that I quoted several times, which indeed quote the paper.
Yeah, Polishuk cites
yes, correct,
AJS, yeah.
And then somehow there is a paper by Niemann that indeed also somehow, So those are exactly. So for us, it's fundamental, this theorem. Somehow, this thing that somehow, you can build as many T structures as you want on quasi-coherentship. It's fantastic. The only thing is that the hard thing is then to descend them somehow. That's an annoying thing, and that's what we do essentially. Somehow that essentially what's the whole point of this thing. Yeah. Thanks for the remark. Sorry, I was quick, so I didn't give all the credit.
No.
So by allusions, have you looked at if your T structures have some nice relationship with the monoidal structure, or this is something you are not interested?
Well, the tensor T structure.
With tensor T structure. Yeah, for us somehow we are. It's true that for us, we are not interested in that, because the T structure that comes, for example, for Bridgeland stability, which is the one that motivate a bit what we are doing here, they do not have, at least not explicitly. They don't have a monoidal structure. So that's a bit. I haven't thought about it. So that's my my answer. So could be nice. Maybe for example, you can prove the conjecture, for example, if you add some more condition. That definitely possible. But for us, somehow our motivation, as I said, was more this kind of tilted things or some weird construction that there are. It's unclear if they have a monoidal structure. Totally unclear, and I would expect not. Well, it depends more, but yeah, it's a good question. I don't know. Yeah.
Okay.
Thanks.
Thank you, Leo. Any other questions, anyone? If not, let's thank Emanuele once again.
Thanks
Great to talk.
again for having me. That's hopefully.
Thank you all of you for coming. We have Vladimir Sosnilo from